In this video, we will practice working with semi-log plots. This is AP Precalculus topic 2.15. If you appreciate this content, please give it a like. This is a semi-log graph because the vertical axis is scaled multiplicatively, while the horizontal axis is scaled additively as usual. In this case, each number on the vertical axis is 10 times the lower number. Notice that the bottom line on the vertical axis is a 1 and not a 0. As we go up line by line, it has a value of 2, 3, 4, 5, all the way up to 10. As we pass the number 10, we have to begin counting by tens. So the next number is 20, 30, 40, and so on, all the way up to 100. As we pass 100, we must count by hundreds. So this line would be 200. The next line would be 300, and so on. Number 1, plot the following points on the same coordinate plane above. The point A is at 0, 5. So we start off at 0 on the horizontal, and this is number 1. So then it's 2, 3, 4, 5, and point A is going to be right here. Point B is 1, 300. So we start here at 1 on the horizontal, and we're going to go past 100, obviously. This is 100. The next number will be 200, and the next number will be 300. So this is point B right here. Point C, 2, 20. So here we are at 2. We must go past 10, and then we count by tens. So this next mark is 20. So this is point C. 3, 150. So here's 3 on the horizontal. We must pass 100, but then we count by hundreds. So the next mark would be 200. So 150 is going to be halfway between 100 and 200. So let's label this as D. And then the point E, 4, 100. So here we are at 4 on the horizontal, and obviously 100 is this line right here. So this is point E. For number 2, we will continue practicing the same skill. Just understand that 10 to the 0 power is 1, and 10 to the 1 power is 10, 10 squared is 100, 10 to the 3rd power is 1,000, and 10 to the 4th power is 10,000. 10, 2,000. So here we are at 10. For 2,000, we have to go past 1,000, and then we count by thousands. So this is 1,000. The next mark will be 2,000. So this is point A. Point B is 22, 250. So this is 20, and then it's going 22, 24, 26, 28, 30. So 22 is at this mark right here. Let's graph 22, 250. We must go past 100, which is right here. The next mark is going to be 200. The next mark would be 300, so 250 will be between these two marks. So this is point B. Point C is 30, 1. Here is 30, and 1 is the bottom line. So 30, 1 is right here. This is point C. Point D is 38, 17. This is 32, 34, 36, 38. To get to 17, we must pass 10. And as we pass 10, we begin counting by tens. So this bottom line is 10, but the next line would be 20. 17 is going to be a little bit below that, but pretty close. So I'm just going to put point D right here. Point E is at 46. This goes 42, 44, 46. To get to 5,000, we must pass 1,000. And as we pass 1,000, we begin counting by thousands. So this line is 1,000. The next line is 2,000, 3,000, 4,000, 5,000. So point E is right here. Number 3, the table above gives selected values for the function g. Which of the following graphs could represent these data in a semi-log plot where the vertical axis is logarithmically scaled? A is a semi-log plot because the vertical axis has numbers that vary multiplicatively. We are multiplying by 10 each time, as in the examples from before. So I'm going to come back to that. Option B only has 2 numbers labeled. That's not enough to tell that the vertical values are varying multiplicatively. This might go 10, 20, 30. 2 values are not enough. So option B cannot be the answer. Looking at option C, the values on the vertical axis are changing additively. We are adding 500 each time. So this is a normal scale. This is not a logarithmic scale. So option C cannot be the answer. Similarly, option D cannot be the answer because the numbers on the vertical axis vary additively. 1, 2, 3, 4. We're just adding 1 each time. This is not a semi-log graph. So I guess we don't have to think about it too hard. A is the only semi-log graph, so A has to be the answer. Just for fun, let's check the first input-output pair. 10, 30 should appear on this graph. So here is 10, and to get to 30, we must pass 10, which is right here. And then as we pass 10, we begin counting by tens. So the next number would be 20, and the next number would be 30. So this is the point 10, 30. So that just verifies for us that the answer is A. The points A, B, and C are plotted on the semi-log plot above, where the vertical axis has been logarithmically scaled. Use the semi-log plot above to answer the following questions. Number 4, the coordinates of point A are most likely which of these? So let's see, A is at 1 on the horizontal. So A is going to be 1 comma something. And then A is after 100. So as we pass 100, we must begin counting by hundreds. So the next mark will be 200, and where A is at 300. So 1 comma 300. So the answer is C. Moving on to point B, it is at 2 on the horizontal, and we have passed 10, so we must count by tens after this. So this is 10, 20, 30, 40, 50. So I'm looking for whatever is 2 comma 50 or very close. It looks like the answer is again C. Consider point C. It is at 4 on the horizontal, so we know it will be 4 comma something. C is after 10, so we must begin counting by tens. The bold line is 10. The next number is 20. So the y value is something between 10 and 20. So maybe it's 14, maybe it's 15, maybe it's 16, something between 10 and 20. As we look down at the answer choices, we actually see 2 values that fit this description, and they're pretty close together. So we have to be careful to decide whether the answer is B or C. Let's zoom in on the values between 10 and 20. Because the vertical axis is scaled logarithmically, the marks between 10 and 20 would not be evenly spaced. They would start out spaced more widely, and then they would get closer and closer as we approach 20. Notice that even though the number 15 is halfway between the value of 10 and 20, on the logarithmic scale, it will be very close to 20 and further away from 10. So this point C, which is closer to 20 than 10, is actually about here on the axis. So it's going to be closer to 15 instead of 16 point something, which would be quite close. So I'm going to go with option B as the answer. Number 7, the function f is graphed on the semilog plot above where the vertical axis has been scaled logarithmically. Which of the following functions could be a model for f? Remember that 10 to the third power is 1,000. So as we pass 10 to the third power, we must count by thousands. So that means that this red dot right here is the point 0, 2000. We can use that point to help us make a model, but we're going to need one more point. So let's look at this point right here, which is 1, 1000. So let's use these 2 points to make the exponential model. An exponential model has the form a times b to the x power. So if we plug in 0 for x, we should get 2000 for the output value. So if we plug in 0 for x, this model becomes a times b to the 0 power is equal to 2000. b to the 0 power is 1, so this is basically gone, and we have a is equal to 2000. So plugging this into the model, we now have f of x is equal to 2000 times b to the x power. To find the value of b, let's use the other point. If we plug in the input value of 1 for x, we should get an output value of 1000. So, plugging in the 1, we have 2000 times b to the 1 power, and that will equal the output value of 1000. Of course, b to the 1 power is just b, and dividing both sides by 2000, we would have 1000 over 2000, which will quickly reduce to 1 over 2. So, putting the values of a and b back into the model here and here, we get f of x is equal to 2000 times b, 1/2, to the x power. Scanning across the answer choices, let me make sure you can see option D. We can tell that the answer is C. Number 8, the function f is graphed on the semilog plot above where the vertical axis has been scaled logarithmically. Write an equation for the linear model for the semilog plot in the form log base n of b times x plus log base n of a. Wait, this is the same graph as before. So we just found the exponential model, which means we just found a and b. Therefore, the semilog linear model will be y equals log base, well, the base is the multiplicative change on the vertical axis. Each value is being multiplied by 10, which you can easily see by the fact that we have base 10, 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3, and so on. So this 10 is the n value. So we could write log base 10 of b because n is 10, but we have learned that base 10 is understood. It is the common log and we don't need to write it. So log base 10 of b will become log of 1/2. And then times x, and then plus the log of a. That's the log of 2,000. So that's it. Number 9. The semilog plot above corresponds to the data table from function g in question 3. And here is that data table. Part A. Write an equation for the linear model for the semilog plot of the form y equals log base n of b times x plus the log base n of a. The a and the b here are the same a and b from the exponential model y equals a times b to the x power. So my strategy will be, let's use input-output pairs to find the values of a and b in the exponential model as we have in the past. Using this first input-output pair to write an equation, if we substitute the input value of 10 for x, we should get the output value of 30 for y. So we have a times b to the 10 power is equal to 30. In a similar way, the second input-output pair gives us the equation a times b to the 20 power is equal to 90. Now we need to solve this system of equations by substitution. On the blue side, we can get a by itself by dividing both sides of the equation by b to the 10th power. So we get a is equal to 30 over b to the 10th power. Now we can substitute this expression in for a of the red equation. So we get 30 over b to the 10th power times b to the 20th power is equal to 90. The b to the 10th power in the denominator will cancel out 10 of the b's in the numerator. So on the next step, we will have 30 times b to the 10th power. Another way to think about it is when you divide with like bases, you subtract the exponents. So you can think of this as 20 minus 10 is equal to 10. So either way, we have 30b to the 10th power is equal to 90. Dividing both sides by 30 gives us b is equal to 3. Sorry, b to the 10th power is equal to 3. So in order to get b by itself, we need to raise both sides of this equation to the 1/10th power. So b is then going to equal 3 to the 1/10th power. Now we can substitute this back in for b right here. b to the 10th power becomes 3 to the 1/10th power to the 10th power. When you raise a power to a power, you multiply. So we have 1/10 times 10, which is 1. These cancel each other out when you multiply. So you are left with a is equal to 30 over 3. In other words, a is equal to 10. Now that we have the values of a and b, we can answer part A and part B. For part A, we need to write y equals the log base n. Wait a minute, what's n? N is the base we are using to scale the vertical axis. So n is obviously 10. Another way to look at it is that n is the multiplicative change between values on the y-axis. So n is 10. So log base n of b is log base 10 of 3 to the 1/10th power. Of course, when it's log base 10, you don't actually have to write the base 10. It is understood. And then it's times x, because this is like mx plus b. So there's your x. And then plus the log of a. So this will be the log of 10. The log of 10 is 1, so we could just put a 1 right here if we wanted to. So that's the answer for part A. For part B, we need to write the exponential model, y equals a times b to the x power. So that'll just be y equals 10 times 3 to the 1/10 power to the x power. So that's it for part B. Number 10. A group of students in Mr. Passwater's class graphed a set of data consisting of the 6 points shown on the semi-log plot above, where the vertical axis is logarithmically scaled. Then they used the data to create an exponential regression model of the form y equals a times b to the x power, where a and b are constants. Which of the following is most likely to be the residual plot from their model? We've learned that if a semi-log plot looks linear, then the function is actually exponential. So that's what we see here. So we know that the data is best modeled by an exponential function. In previous videos, we have also learned that if you use an appropriate regression model, the residual plot should have no clear pattern. The students used an exponential regression model. And because the semi-log plot appears linear, we know that the data represents an exponential function. So an exponential model is appropriate. Therefore, the residual plot should show no clear pattern. Which of these residual plots shows no clear pattern? The answer is B. This residual plot is the only one that shows no clear pattern. This indicates that an appropriate model was used. Hey guys, don't forget to like and subscribe, but also if you found this video helpful, there's a lot more where that came from. You can click the upper link, which will take you to the whole unit playlist, or you can click the lower link, which will take you to the next video in the playlist. See you there.